Good morning, everybody. My name is Danesh Burket. I am R&D Director in the Research Center Řeš. I hope you can hear me, you can see me. It's a great pleasure for me to welcome you to the traditional SUSEN conference, which is dedicated to presentation of the outputs of the SUSEN project and related invited presentations. This year's conference is exceptional in its form because due to the situation around us, we were forced to organize this conference in the form of a webinar, but I believe it will not affect the quality and will still benefit all participants. I would like to thank all those who participated in the organization of the conference, invited presenters, and all presenters in the oral and poster section. Let me note that the articles related to the presentations you can find in the special issue of the Nuclear Energy, in the Czech language, Jaderná energie journal. And now I would like to give the floor to Jana Kalivodová, the scientific secretary at the Research Center Řeš, who will moderate this conference. Please, Jana, the floor is yours.
Okay. Good morning, everybody. Thank you very much. Thanks to Danesh Burket, our director for research and development, for the welcome speech. And now we would like to give floor to our first presenter, Lorenzo Malerba, who is, among other function, coordinator of the joint program Nuclear Materials under the ERA. So please, Lorenzo, if you are on, floor is yours.
Okay, good morning, everyone. I hope you can hear me. And I hope you can see my screen because I'm not 100% sure. Can you confirm that you see my presentation? Hello?
Lorenzo, you are on. You have the presentation.
No,
we can see it.
Sure. Okay, good.
But just not in the presenting mode. So just to switch it to presenting mode. And if you allow me one more thing, if you all people have some question, you can write them please in the chat. Thank you very much. Please, Lorenzo. Thanks a lot.
Yeah, thank you. I think I need to change the screen that I share because okay. All right, so I think it should be okay now. So good morning, everyone, and thank you for inviting me to this SUSEN conference 2020, even though the conditions are, the circumstances are what we know. I've been asked by Jana to provide a sort of overview of the research on nuclear materials in Europe from the point of view of the ERA joint program on nuclear materials that I coordinate, and so I tried to put together some information about this. First thing I would like to do is to say what is ERA, because not everyone maybe knows what it is. It stands for European Energy Research Alliance. It is, in fact, the largest energy research community in Europe. Legally speaking, it's a non-profit association, and at the moment there are about 250 members between universities, public research centers located in 30 countries in Europe, both belonging to the European Union but also associated. And the way of working of ERA is through so-called joint programs. There are 18 at the moment, and they cover a wide spectrum of research activities. All low-carbon technologies are represented, and there are also aspects related with systemic or cross-cutting topics. The structure of ERA is the typical structure of an association. The important point here is that you have all the joint programs that are basically the backbone of this association. And the joint program on nuclear materials is just one of the 18 joint programs of ERA. Now, to try to explain to those who are familiar, and especially those who are not familiar, the complicated situation in Europe in terms of platforms, associations, and so on. I will remind you, in Europe, the European Union is based on 2 treaties, not just one. One is the normal one, the EU Functioning Treaty, but there is also a Euratom Treaty, which is a separate. Now, for what concerns energy research, about 13, 15 years ago, the European Union created the so-called SET plan, or Integrated SET plan, Strategic Energy Technology Plan, with the idea of coordinating the low CO2 emission energy research in the EU. And this basically is an initiative of the member states, even more than of the Commission. The Commission facilitates this, but the member states are those involved. So the creation of this SET plan motivated the creation of a large number, in fact, of platforms or associations. Sometimes these platforms are actually legally associations, sometimes not. Mainly, these platforms are industrial platforms that now, originally maybe not, are called European Technology and Innovation Platforms. ERA was created essentially as a response to these industrial platforms, because it wanted to be the voice of the public research organizations as opposed to industry. And it is based, as I said, on these different joint programs. And one of them, they try to connect with the ETIPs, with the technology and innovation platforms. And one of them is the joint program on nuclear materials, which is, however, a little bit different from the others because we work a little bit on the other side. So we are connected with the Euratom Treaty. If we look at the situation under the Euratom Treaty, there is also an ETIP, a European Technology and Innovation Platform, which is called SNETP. Recently, it became a legal entity, and it is a very large association in the nuclear field, which has 3 pillars. One dedicated to Generation 4, ESNI, one to Generation 2 and 3, Eugenia, and one to cogeneration and CTY. And then there is Eurofusion, which is not an association. It's in fact a European joint program funded largely by the Commission and the Member States, but it is also an important actor in the nuclear field under the Euratom. So the joint program on nuclear materials initially was created to support ESNI, to support the pillar on Generation 4 of the SNETP. So it's a little bit on the other side, or depending in a way on a different treaty, but with a strong connection with ESNI. But then we basically enlarged our portfolio, and we try to find connections with Eugenia and also with Eurofusion as much as possible. And in 2016, a memorandum of understanding was signed with the SNETP, the whole of it, to strengthen this link that otherwise was a little bit difficult, being the JPNM in, let's say, under a different position. So the origin of the joint program on nuclear materials was exactly to support sustainable nuclear energy, meaning Generation 4 systems. And we have to go back to the situation in 2010, when 4 industrial projects were identified. Astrid, which is supposed to be a sodium-fast reactor prototype, Alfred, a lead-fast reactor demonstrator, Allegro, a gas-fast reactor demonstrator, and Mira, not a reactor, but a facility for irradiation based on generation 4 technology for transmutation. So in this landscape, technological landscape, there was a large project in those times from 2008 to 2013 called GetMat, which stands for Generation 4 and Transmutation Materials, that tried to provide research for these 4 systems in a cross-cutting way. It was a large project, and it coincided in terms of timing with the creation of ERA. ERA was actually created in 2007, but in those years it was growing as an initiative. So in this framework, it was decided to create, on the one side, ESNI as a pillar of SNETP, which included these 4 industrial projects in a platform. But since there was no activity on materials included explicitly in these projects, the joint program on nuclear materials was created in the framework of ERA in 2010 at the same time as ESNI. And then we had, as a first project in, let's say, under the umbrella of the ERA joint program on nuclear materials was Matter in 2011-2015, which was dedicated to design codes and design rules for the pre-normative research on materials for the 4 systems of ESNI and later Matisse. So at the beginning, the idea was to essentially, within the joint program nuclear materials, to move from basic and applied research to technological innovation and to industrial application towards basically the Generation 4 prototypes and demonstrators. So according to this idea, the ERA joint program was created initially focusing on structural materials and with 4 sub-programs. 4 sub-programs that moved from a fundamental modeling to the development of new materials, innovative steels, mainly oxide dispersion strengthened steels, and refractory materials, in those times mainly silicon carbide composites, and provide support to ESNI by qualifying existing materials. So this was a very simple structure, maybe very focused, maybe too focused, because it had already chosen a number of materials on which to basically focus their research. But in fact, this was going to grow. This was the situation when the project Matisse included basically 4 work packages, each of them dedicated to one of these programs. Later in 2014, the portfolio was increased by adding fuel. And so 2 sub-programs more were created, one dedicated to advanced fuel, closer to ESNI applications, and another one dedicated to modeling. So again, the idea was the same, but in this case, there was a single sub-program dedicated to both support to ESNI and new fuels. And then over time, there was an evolution. This is the timeline from 2008 to 2014. It was FP7, then Horizon 2020 started, and now we are about to see Horizon Europe start, even though probably with some delay. So we had this big project GetMat in FP7 from 2008 to 2013, which was a little bit the cradle for the creation of the ERA joint program on nuclear materials. Matter was devoted to materials testing and rules, so as I said, was design rules. And at the same time as Matter was prepared and launched, started also the idea of having internal projects to the ERA JPNM, which were going to be the base for the different projects that later on were, let's say, asked to the Commission and obtained. So Matisse was, as I said, a project where all the 4 sub-programs that we had on structural materials in 2013 were funded. It was called Materials Innovation for a Safe and Sustainable Nuclear in Europe. It had also a strategic part, in fact, inside, which was the consolidation of the joint program as a platform within ERA. And after that, based on the pilot projects of the joint program nuclear materials, 4 projects were launched. And now you can see already an enlargement in our portfolio, because we had GEMMA, we still have, it is still ongoing, which stands for Generation 4 Materials Maturity. This is dedicated fully to the materials that should be used in the ESNI prototypes, at least those that are still on the table, because some of you may know that Astrid has been shelved for the moment. There is a difference between matter and GEMMA, even though they are connected somehow. And the main one is that in matter, ferritic martensitic steels were still, let's say, maybe not the most important, but a big part of the research in Generation 4. In GEMMA, austenitic steels have become the focus, because it has been recognized that the prototypes will use materials on which there is already experience. So this is a difference, an evolution that happened during this time, moving towards a clearer design of the systems. Inspire is on fuel, because we introduced fuel in 2014 in the portfolio. So it's dedicated to MOX in support of ESNI, because most prototypes in ESNI will use MOX. And there is also this multiscale modeling for fusion and fission materials, which includes the word fusion. Basically, this is a cross-cutting project, and it shows how we are also let's say, collaborating with other communities, in this case, fusion. And the research on ferritic martensitic steels has now moved in this framework, because these materials are common to fusion and fission. Horizon 2020 is, will continue, the projects will continue until about 2024. And now Horizon Europe is going to start. And as a last action within Horizon 2020, the Orientenem not project, because it is not a research project, but a coordination support action, has been launched, and I will talk about it. It tries to prepare a European partnership on nuclear materials, starting hopefully in 2023 or 24, which should include all the, or most, research in Europe on nuclear materials. And it is important to introduce Nugenia at this point, because Nugenia is, let's say, our counterpart in Generation 2 and 3. Nugenia was created in 2011, so more or less all these platforms were created at the same time as the Generation 2 and 3 pillar of SMETP. And it is important because it is the only other nuclear platform among all those that I shortly presented before that includes activities on materials. So over the last, let's say, 10 years, more or less, in the framework of Nugenia, a number of projects were launched dedicated to materials. And of course, here we are in the world of Generation 2 and 3. So the main topics were embrittlement of reactor pressure vessel steels, of course, in the framework of long-term operation, environmental effects on austenitic steels, the internals. But these were, let's say, the classical, I would say, topics of materials in European projects, also before 2010. But now it is clear that there is also an increase in terms of portfolio towards polymers, also towards concrete. I did not include it, but now there are also projects that are about to start or maybe already started on concrete. Advanced inspection is becoming very important. And also, in fact, advanced manufacturing techniques, and anything related, of course, with structural integrity assessment and performance is essential for Generation 2 systems. So, what is the difference and what are the commonalities between Generation 4 materials and Generation 2? This is a graph that you might have seen already. It's a very interesting one that was introduced by Steve Sinton years ago, where you see the temperature, operation temperature, and the displacement damage in dPa as a measure of exposure to irradiation. So on this graph, current reactors, Generation 2 and 3, the vessel will see a very, very small, let's say, dose in terms of dPa, and temperature also relatively low. Generation 2 and 3 core internals might reach relatively high doses, maybe up to 80 dPa, but temperature, of course, remains in the range of operation of current reactor. We all know that when we move to generation 4, we need to go to higher temperature and higher dose. And these are the ranges that are common to fusion. So basically, the materials in generation 4 are sometimes common with generation 2 and 3, for example, austenitic steels. However, they are expected to withstand much harsher conditions, so somehow they create a link also with fusion. Essentially, what we need for generation 4 and fusion are materials resistant to high radiation dose, high temperature, and corrosion. But it is important to realize that this is not, even though the conditions of nuclear energy are specific and we have irradiation, of course, entering in the picture, but in fact, most high energy density technologies need materials resistant to high temperature, and this is very important in the framework of ERA to realize. Several techniques, energy technologies need to increase the thermal efficiency because this indirectly reduces CO2 emissions and also minimizes the use of resources because you extract more energy from the same amount of fuel, whichever the type of fuel you want to use. So this is important to increase the thermal efficiency, of course, for nuclear, for so-called clean fossil, for example, coupled to carbon capture and sequestration, or reuse in some cases, and solar and biomass as well. Renewables will be intermittent, so especially solar will be subjecting materials to fluctuations in temperature. So this means also need of resistance to temperature effects in terms of oscillation, so creep fatigue, and this type of effects. And then there are some processes that inherently need high temperature, so solar furnaces, for example, or advanced electrolysis and catalysts for, it can be batteries, it can be fuel cells, or deep underground geothermal. This is also something that includes contact with very high temperature fluids, in this case, supercritical water. So it turns out that the need for materials that resist high temperature in a broad sense, including also corrosion effects, which are exacerbated by high temperature, there are several of these. So fuel cells and hydrogen, concentrated solar power, bioenergy, geothermal, as well as nuclear, find commonalities in the need to operate at temperature higher than 400 degrees C. All these technologies, and partly nuclear as well, nowadays are also faced with the constraint of circularity. So circularity basically means that we need to consider from the start the problem of resource scarcity in each stage of the life cycle of any component or device or installation used for energy production. In this case, of course, circularity affects any kind of technology and industry, but we are talking about energy here. So it means considerations about raw materials, the availability of raw materials, extension of component lifetime, reuse and recycle as much as possible, minimize waste, consider the environmental impact. It is interesting that these issues, in several cases, have been faced by nuclear energy even before there was a talk about circularity because of the inherent needs of nuclear energy. In general terms, nowadays, any energy technology has to look at this, let's say, type of drawing of circle and analyze it very carefully in order to minimize waste. So in a recent series of documents that have been produced as a basis for the Clean Energy Transition Partnership, basically 3 main topics have been identified related with circularity. These are raw materials, which means to take into account whether or not a material that you want to use is sufficiently available on Earth to allow this certain technology not only to be deployed, but also to continue over the decades and the centuries. reduce geopolitical dependency, and make extraction socially and environmentally acceptable. I insist on the fact that aspects of scarcity, abundance of elements, and especially the reduction of geopolitical dependency are aspects that nuclear energy already started to face, let's say, a long time ago. Maybe the raw materials a little bit less, the scarcity or abundance, but this is done certainly in fusion. There is a need to increase the component lifetime. Again, in nuclear, this is very, very well known for some time. In other energy technologies, they kind of discovered it recently. So there's a lot of work on life cycle assessment, but I think it is time to move towards life cycle improvement. And this goes through the development of advanced material solutions and advanced innovative fabrication processes. And there is the third aspect, which is reuse and recycling. Reuse and recycling implies choosing materials, having in mind the possibility of reusing or recycling, design the component in such a way that it can either reuse previous parts or be recycled through, for example, easy dismantling, making it easier to collect the waste and reprocess it. There are also legal aspects that I will not go into, but of course you need them, and to incentivize recycling and reuse and regulate correctly. So all these things are, in fact, we need to take them into account for all energy technologies and nuclear as well. Another aspect that is related with circularity, and it is important in nuclear and it is becoming important for other energy technologies, is materials health monitoring through non-destructive examination and testing. So in the past, this was something relatively simple. So the idea is when you, it was just about detecting defects in components to assure quality. So when the component is produced, you need to basically give some guarantees that it is apt for use, so there are no defects in it. And during operation, there was some sort of plan of inspections and nowadays, this again is becoming something circular where you have to take into account all aspects from raw materials to the way the components are developed, produced, and especially during operation. So what does all this mean? It means that the constraints and the expectations on materials that are used for components are becoming more and more. And therefore we need new material solutions. And another new trend that we have to take into account is the one towards so-called accelerated autonomous material optimization or even discoveries. So the idea here is to have a platform that ideally, this is maybe a little bit science fictional, or it looks science fictional, but by producing in a high throughput, let's say, framework, so with high efficiency, a number of different materials that are automatically characterized and tested and collecting a lot of data, by producing suitable models, it is then possible to close the circle and improve or even discover, improve progressively the material or discover new materials. Using what? Using something that is very modern or at least on fashion right now, machine learning algorithms, robotics, pattern recognition, again based on artificial intelligence, developing representative fast tests, especially at the micro or even nanoscale, and good management of data, guaranteeing data quality, representativeness, metadata, and so on. This is a little bit science fictional, but in fact it is already happening for some applications, for example, the production of nanotubes and also materials for batteries. So basically, and I'm going to get to closing my presentation, there are a number of issues that need to be taken into account. The clean energy transition, which includes nuclear, needs to be reliable and circular, efficient, cost optimal, and to make this possible, it is necessary to use new technologies, new techniques. So, for example, advanced manufacturing, accelerated qualification, health and monitoring using non-destructive examination and testing, artificial intelligence and robotics, advanced characterization, modeling, data analysis, which means essentially new material solutions obtained using these techniques. So in this framework, obviously, also the research on nuclear materials needs to evolve. In part, nuclear materials research already anticipated some trends because they were inherent to nuclear energy, because of the safety constraints or because of the need to take into account the full cycle of the fuel. This is something not new in nuclear, but we all know that nuclear is also a little bit suffering from the lack of innovation in several ways. So we started off in the joint program on nuclear materials with a relatively simple, if you want, a structure where we were looking at two types of materials, structural and fuel, and applying three, let's say, so-called infra technologies or approaches, so qualification, development of advanced materials, and modeling and microstructural characterization. And now with OrientNM, which I mentioned earlier as a coordination support action that just started to prepare a partnership on nuclear materials, we are widening the spectrum. This also because we need to include not only generation 4 materials, but also generation 2 and 3 materials. But it is not just a matter of increasing the number of materials, it is also a matter of increasing the approaches and technologies that are used for the research on these materials. So it is not only qualification, let's say, processing and development and modeling. We need to look at the non-destructive examination part. So we need to take it into account even when we develop a new material in a way, the possibility and design a component, the possibility of applying this type of online monitoring, for example. We need to take into account the need for standardization, quality assurance, and especially knowledge and data management, and all the other aspects that here are summarized as cross-cutting, but in fact they include the use of artificial intelligence, these new trends that we need to include also in nuclear energy. So in this framework, this OrientNM initiative that just started tries to provide a vision on the future of nuclear materials. It is an alliance between the ERA Joint Program on Nuclear Materials and SNEPC and Eugenia to prepare a European partnership on nuclear materials, which means, first of all, to achieve a single vision on nuclear materials research until 2040 and produce accordingly a strategic research agenda that should take into account all the constraints, industrial, member states, priorities, and so on, but also provide an efficient governance and legal structure. Important are the aspects related with intellectual property issues and innovation, and interact with other stakeholders. Nuclear materials involve, in fact, activities at several levels, international organizations, standardization bodies, collaboration with other energy technologies, so all these aspects. And so with this, I conclude. I hope I managed to give you an idea about the evolution, let's say, of materials, nuclear material research in Europe in the last few years. Thank you.
Okay, thank you, Lorenzo, very much. Thank you for your presentation, for the very nice introduction to our European research regarding nuclear materials. Since there is another presenter waiting and we are quite nice on time, I think, and there are no questions posted so far, people probably are still thinking about them. So I think that we will give the word to Maria Zimena, who is our next presenter. It's an employee of CVR. Please, Maria, if you can connect, we are
thank you,
happy
Jana.
to. Okay.
Can you hear me clear?
Very good, thank you. Soon
Great.
maybe we will see also your presentation.
Probably. Okay.
Yeah, it's coming. If you can try.
Okay. So
perfect. Now we can see something wonderful.
I hope it's presentation. Okay.
Very good. So thank you,
So it's
Maria.
a full screen now, right?
Yes, you are on.
Okay. Okay. Thank you, Jana. Thank you, everyone, for joining our conference. And today, I hope you're all good and doing well during these strange times. And to make these times better a bit, I would like today to present our work with my colleagues Anna Hoyne and Jaromir Janošek from CVR, which we have been performing during past 3 years, I guess. And this is the effect of surface treatment on the environmental assisted corrosion initiation of steel in high temperature water cooled environments. This work is performed in a frame of research for SUSEN and Horizon 2020 MEACTOS projects. MEACTOS projects is one of these European projects which deals with mitigating environmental assisted cracking through optimization of the surface treatment. And further, I will tell you how. And so today I will be particularly focusing on the acceleration of the environmental assisted corrosion under laboratory conditions in order basically to establish the numerical model for the prediction of the corrosion behavior of the stainless steel and some nickel-based alloys under operation conditions of the primary circuits of light water reactors. So I will introduce our new autoclave systems for low pressure superheated hydrogen steam environment and also simulated pressurized water reactor environment. Those two facilities were built during the SUSEN project. The pressurized water reactor environment autoclave is located in Rzeszów, and this system for the superheated hydrogen steam is in Pilsen. Also, I will focus on some recent results which we already obtained. So to investigate the stress corrosion tracking in operation conditions, we need to perform a long-term expensive laboratory testing, which first of all are not so statistically reliable, and they are very financially disadvantageous, which means it takes a lot of time, and in nuclear industry we basically don't have years of testing to prove that the material we already use is good. So that's why the concept of accelerated testing appears to be very useful for this case, and we can have, instead of years of testing, we can build a prediction model for material behavior, which is based upon a number of factors, which are, for example, temperature, where we go in from 3020 centigrades of operational temperature to 350 or more, as you will see during my presentation. And the other factor is the strain rate, where we go from the nearly steady state of operation to higher strain rates up to 10 in the power of 6 reverse seconds or so. And the acceleration can be also done using, for example, more pronounced environments such as hydrogenated steam vapor instead of PWR environment. It was shown earlier by Economy et al. With the nickel alloy 600 in high pressure water at 320 centigrades and high pressure steam at 400 centigrades. They have indicated similar corrosion behavior between those two environments. So since then, basically those tests in the hydrogenated steam are widely used as a procedure to predict cracking in PWR. Also, the effect of surface treatment on the environmental assisted corrosion is the main goal of the MEACTUS project I've already talked about. And so for this investigation, we in the MEACTUS project, we use two types of materials. The first one is a nickel-based alloy 182. This materials was chosen to study the EAC resistance of new surface treatments applied for this alloy, and also the conventional 316L austenitic stainless steel. It was used more to gain new data on the components manufacturing methods and their resistance to the environmental assisted corrosion. So I will be more focusing on the stainless steel part, and I will show you some results we gained during these years with my colleagues. So we use the 15 millimeter thick hot rolled and solution annealed plate of the stainless steel. Here you can see the microstructure of the plate. It has an average grain size of about 30 micrometers. It also has beta ferrite stringers distributed along the plate in the rolling direction. And here you can see some mechanical properties of the plate. So we have manufactured so-called flat tapered specimens. Here you can see the shape of the specimens. This shape is used to allow to calculate the threshold stress, which is minimum stress enabling the environmental assisted corrosion initiation. So owing to this taper shape of the gauge, we can determine the threshold stress of the test specimens from the location of the last crack along the gauge lens. Also, we use two surface finishes of the specimen. One is a polish laboratory finish using 1 micrometer diamond paste, and the other one is a ground surface, which was also grind in laboratory up to 500 grit paper. We also measured the roughness and the micro hardness of those surfaces, and also the residual stresses of both surfaces were measured by XRD technique. Here you can see the results, and The compressive residual stresses were found on the polished surfaces from of about minus 300 megapascals, and for ground surface it was a bit different, which corresponds to, as you can see here, it corresponds to the grooves during the grinding procedure. Also on the ground surface, one can see the deformed layer under the surface caused by the grinding, and so we applied the constant extension rate tests to this specimen with two extension rates, S1 and S2, as you can see here, to investigate the effects of the extension rate on the initiation. We used two environments, as I mentioned before. One is a simulated PWR environment with no hydrogen addition, which revealed the nickel oxide stability conditions, and also the hydrogenated steam vapor, which is in exudation condition. Those environments can be described with the coefficient R, which is when it's less than 1, it's stable. The nickel oxide is stable under this condition, and if it's more than 1, the nickel is stable, so it's a reducing environment. So during the SUSEN project, facilities were built. First one is, as I said, in Rzesz, and it's autoclave system with the water loop, which allows us to perform tests up to 350 centigrades in the simulated water environment. We have a control of the medium during experiment. We measure conductivities, oxygen concentration, flow rate. We can also now newly add the hydrogen into the system and simultaneously apply mechanical loading up to 50 kilonewtons. The other system we use is this system for the hydrogenated steam vapor. This system is located in Pilsen. This cell was originally developed by the University of Manchester by Dr. Stenini, and they also kindly helped to build the same facility in CVR. This testing system consists of a test chamber where we have a cold heat exchanger. Also, we have a fluid filling system where the water is heated up and then the steam and the gas mixture are blended. And it also has the loading system. It is a creep testing machine from Zwick company. So this is what we use for our testing. And to go straight to the results, here you can see the stress strain curves of our specimens in pressurized water and hydrogenated steam vapor, and also the reference is a curve in the air. So what we can see is that we have in the pressurized water, we have a maximum stress of about 400 megapascals, and on all curves we can see those oscillations. We can also see it in the air on the black curve here. And this is not the effects of the environment, but the dynamic strain engineering under these temperature and strain rate conditions. So what we can see here is that the hydrogenated steam vapor behavior is similar to the air and basically similar to the pressurized water. We also performed the SEM observations of the PWR and hydrogenated steam vapor. We found the oxide layer in the water environment and deformation on both ground and polished sides of the sample, and slip bands were pronounced on the polished surface. The micro cracks were found in the region of high plastic stress in the narrowest part of the tapered sample, and we also found the cleavage-like mode on the crack faces on the ground side. The deeper cracks were initiated from the polished side of the sample. We performed also focused ion beam investigation to find the depths of the cracks. On the other hand, on the specimen after hydrogenated steam vapor testing, we found only sporadic oxide particles of various size on the surface. On both surfaces, we also found the slip bands emerging from the surface on the polished and the ground side, and we found only several ductile cracks initiated from the slip bands, basically only on the ground side of the sample, and we didn't find any environmental assisted corrosion cracks. And basically the ground and polished appearance is similar after this testing. So to make a bit of summary after testing at the same temperature in two different environments with two different strain rates, we can say that typical cleavage-like initiation and propagation was observed on the ground and polished surface after testing in PW water. The lower threshold stress was observed on the ground surface compared to the polished one at the same strain rate, but deeper cracks were initiated from the polished surface in comparison to the ground one. Also, after the exposure of this steel to the hydrogenated steam, we used two different test rates. We didn't find any EAC cracking initiation. However, after testing at high temperature, we found more extensive oxidation, and the specimen were also found to be more sensitive to EAC. On the polished surface of the specimen loaded by the lowest test rate, there were observed cracks showing mostly intergranular morphology, and on the ground surface there were observed only transgranular cracks. They were also sometimes arranged in typical clusters, and we also found some ductile cracks. When we were talking about the highest strain rate on the polished surface, we were observing many short intergranular cracks. They were more open in this narrow gauge region, and less open towards the wider end of the taper gauge lens, and we didn't observe any ductile cracks. On the other hand, on the ground surface, many short cracks were observed, and they were also grouped in the clusters. Those baby cracks we found on the ground surface were classified as ductile after FIB investigation. So as we can see, with the high temperature, we observe cracking, and this cracking is more similar to the one which is observed under operation conditions of the power plant. So to conclude, we also performed more testing at different temperatures. The detailed results are presented in our paper, which you can see down on the slide. So in this hydrogenated steam environment, the oxidation increase, and we see the typical intergranule cracks, and at both 400 centigrades and 440 centigrades. When we go to the higher temperature, we also observe oxidation and cracking, but these morphologies, they do not correspond to the mechanism which we observe usually at the PW operation conditions. And so the high accelerated testing suitable for studying early stages of EAC. We need to test at 400 centigrades. So that was the conclusions for the acceleration, and I would like to also to say something about the general results which we expect from the MEACTIS project. We expect to find the effect of the temperature on the initiation of the EIC. We expect to, as I already presented, we clearly can see this effect. We also expect the effect of strain rate to be a strong accelerating factor for the cracking, and the effect of the environment that was shown before. Also the effect of surface treatment, which is the aim of the MEACTIS project. We see that we saw that the polished surface is more susceptible to EIC than the ground, and in the MEACTIS project we use more advanced machining techniques which we investigate. It's a machining with supercritical CO2, with lubrication or without lubrication. So here I just put some examples of the surfaces. It's a standard industrial technique of the surface of the sample. You can see an ultrafine grained layer under the surface of the sample, and this is an advanced machining, supercritical CO2. This, and we expect as the end of our project, we expect to come up with a numerical model of the acceleration of the EIC. And at this point, I would like to thank you for your attention, and I'm happy to answer your questions if you have any. Thank you.
Okay, Maria, thank you very much. Thank you for your nice presentation. So far, I don't see any question in the chat. I strongly recommend to everyone to just write. If there are none, we can move to the next presentation. So the next presenter is okay. So thank you, Maria, one more time.
Okay, thank you.
So our next presenter is Dr. Eugene Sanon. He's a guest professor at the Osaka University. He's also program manager of Institute of Molecular Science, technical advisor of Toshiba ECC Corporation, and R&D director of a venture company LaCube. He is the advisory board member of some national projects, laser projects. So today he will introduce us his research related to the material mechanical properties of stainless steel and nickel-based alloys and shot-peen laser effect. So if we have a connection, please. Professor Sano, are you there? Can we hear us?
Sorry, I cannot.
So we can hear you. That's great. So yeah, if you can switch your camera, because yeah. Maybe in between, I heard from my colleagues that there was some question still to Maria. So before we go to the next presentation, Maria, are you still there? There is a question for your presentation related to temperature and your investigation. And the question is, does it have sense to investigate process for much higher temperature? Okay, it's from Evgen Novak.
Okay, it depends. Yeah, it depends on what in the hydrogenated vapor as it was shown, like at high temperature, even at 480 centigrades, we don't see the same behavior, same mechanism as we want to investigate. So under the operation conditions, so for us it doesn't make any sense in this case. So yeah, if I understood the question right, so no.
Okay, so we can maybe have some more minutes for discussion after the presentation, after the last presentation of this session. So now we would like to move to our presenter, Dr. Sano. Are you already there, please?
Yeah, thank you very much for inviting me this conference. So can you hear me? Can you see the second slide? This is Collaborators. No, this is better. It's okay.
If you press F5
yes.
on the top key, it will go
yes.
to the big large screen. But like this, it's also okay.
It's okay. So this is my collaborators in Czech Republic and in Japan. So I'm very happy working with Hyrates in Czech Republic because they have the world prominent lasers, industrial lasers in the world. So it's okay. So my presentation consists of these. So at first I want to introduce the overview of the LSP. And the second one is I want to explain the effect of laser shock peening LSP on residual stresses and the stress corrosion cracking susceptibility of austenitic stainless steels and nickel-based alloys. Then I'll move to the development LSP system and applications to reactor components of nuclear power reactors to prevent stress corrosion cracking. And finally, I want to explain the effect of LSP on residual stress and fatigue property of 12 chrome stainless steel or low pressure steam turbine blades. So, as you know, the failures of structural components is almost always due to stress corrosion cracking or fatigue. So these cracks usually start on the surface and propagate into inside. Therefore, impartment and upkeep of residual compressed residual stress on the surface are effective to enhance structural integrity together with material and environmental control. To induce compressed residual stresses, we develop LSP, which in which irradiated laser pulses to components covered with water without any surface preparation, and have applied it to nuclear power plants since 1999. So I moved to the LSP technologies. So this graph explains what is pinning or laser shock pinning. So pinning is a technique which makes a force pushing together. It means the compressive residual stress on material components by tapping the surface, like the work of blacksmith. Compressive residual stress on the surface has a favorable effect to prevent the initiation and the propagation of cracks due to fatigue or stress corrosion. Shot pinning is a very famous familiar technology used in the automobile or aerospace industries. The shot pinning can strike the surface by hitting the accelerated small steel shot. So laser shock pinning uses laser shot instead of the steel shot. However, this process is a deterministic process, so we can expect repeatable and reliable effects compared to the shot pinning. So this video will explain how to induce a compressive residual stress by laser. So if we irradiate the laser pulse to focus to a material covered with water, metal plasma forms on the surface through ablative interaction between the laser pulse and the metal surface. So water confines the plasma, increasing the pressure up to several gigapascals. Shock wave is generated due to the high pressure plasma and propagate inside to create permanent strain. A compressive residual stress remains on the surface after the passage of the shock wave. So this view graph shows the effect of the water to confine the plasma. So in this experiment, we irradiate the laser pulse to the material underwater. You can see the plasma here. The diameter is about 1 millimeter in this case. So plasma, this high pressure plasma expands very rapidly if you irradiate the laser pulse to the materials in air. However, water can confine the plasma like this. So laser energy concentrated in a narrow space, it increases the plasma pressure significantly, up to several gigapascals. So this one is a typical setup of our experiment. So here is a laser system. A laser pulse was delivered by mirror and irradiated to the material, submerged water through the lens and the windows. So in this case, we drove the specimen two-dimensionally to cover the certain surface to make a compressive residual stress like this. And then we measure the residual stress by using the X-ray diffraction technique. So this one is a typical experiment in our lab. So here is a small plasma. This one is a laser beam. In this case, material was drove two-dimensional. However, of course, in actual application, we drive the laser beam itself. So then I'll move to the effect on the residual stress and the stress corrosion cracking. So we irradiate the laser pulse with such conditions to the material, in this case, SUS304. The result is like this. So horizontal line shows the depth from surface, and the vertical line is residual stress. So before irradiating laser pulse, we ground the surface to make a tensile residual stress like this, and then irradiate the laser pulse to make a compression like this. So you can understand that LSP can induce the depth of 1 millimeter or more. So if you compare this result to that of the shot pinning, so you can understand the laser pinning can induce a much deeper compression compared to shot pinning. And so that's why because if you calculate the kinetic energy of each shot in shot pinning process, assuming the 1 millimeter diameter of steel shot, and traveling speed of the several tens of meters per second. The kinetic energy is only 1 millijoule or less. However, in case of laser beam, we can irradiate laser pulse with much larger energy, so we hit the surface much harder. So that's why we can induce compressive residual stress much deeper compared to shock beaming. We can adjust the depth of the compression by changing the condition, laser irradiation condition, typically the laser pulse energy. So this one is the typical accelerating stress corrosion cracking test results of SUS-304. We repeated such an experiment by changing the laser irradiation condition, and we determined a certain window which can induce compressive residual stress and prevent the initiation of stress corrosion cracking. After the confirmation of the effect of LSP to prevent the initiation of SCC, sorry, this one is the result of the result on the nickel-based alloy 600 and alloy 182. Similar to the SUS-304, we can prevent the initiation of stress corrosion cracking by LSP. So let's move to the LSP system and application to actual reactor components. So after the confirmation of the effect, we design and construct such a laser beaming system to apply the nuclear power reactor, in this case, boiling water reactors. So before applying the actual application, we did training of the operational personnel and also the full-scale mock-up. And then we started the actual application to the nuclear power reactor. So we put the laser system here and deliver laser pulses through such a waterproof piping into the reactor and reactor core shroud. So this was very successful. However, the accessibility was limited due to the rigid piping for laser delivery. So then we developed an optical fiber delivery system to increase the accessibility to the nuclear power plant. Basic development, and also we did the accelerating gamma ray radiation testing like this. And then we did the laser shock peening experiment with fiber delivery like this. And so we designed the whole system to apply fiber delivery, the LSP to nuclear power reactor, and then actually construct the system. So the target component is the bottom part, weld, this green part, and we did the full-scale mock-up like this. Thanks to fiber delivery, we can follow the three-dimensional shape of the components like this. It cannot be done by the pipe delivery system. So LSP with fiber delivery has been applied to nuclear power reactors successfully since 2002. So we also applied laser beaming to pressurized water reactors. In this case, the BMI nozzles. BMI means the bottom-mounted instrumentation. So we developed a pencil type of very thin optical head like this, and this one is the basic experiment. And we pinned the inside of such pipe and actually applied to the nuclear power reactor PWRs to the inside wall of the BMI nozzles. And also we applied the laser beaming to the outside wall and this weld by LSP like this. So we did actually laser beaming to PWR since 2005. So This one is the example of the LSP application to Japanese nuclear power reactors. We did the LSP more than 10 nuclear power plants in Japan. However, the Fukushima accident in 2011, we stopped every application to the Japanese nuclear power reactors. However, recently we did the LSP to the PWR, in United States, Arkansas Nuclear One. So let's move to the enhancement of high cycle fatigue of the turbine blade. So you know the turbine missile accident sometimes occurs. For Japan, in Japan, for example, about 50 years ago, turbine missile accident occurred. And the fragment flew about up to 380 meters away from the plant. So it's dangerous. So recently, in 2011, in South Africa, they had such accident, tragic accident, during the overspeed testing of turbine system. So in nuclear power reactor, we experienced such accident, such event in Japanese nuclear power reactor BWRs. So you can see the turbine blade, long turbine blade dropped off from here, from the turbine rotor. So the cause was identified as a high cycle fatigue failure of the fork due to vibration during operation with huge centrifugal force. So at first we did the experiment of LSP to confirm the effect on the residual stress, and then did the fatigue testing like this. Anyway, the result was successful, encouraging. So we construct a system to apply the LSP system to the turbine blade, especially for the inside wall of the fork part. So actually in Japan, we experienced the drop-off of the turbine blade due to the fatigue crack initiated from the inside wall. So that's why we developed a very small optical head similar to that for the PWRs, and pin the inside of each holes of the long turbine blade. So let me conclude my presentation with this view graph. The positive effect of LSP on residual stresses, stress corrosion cracking susceptibility, and fatigue properties were confirmed for stainless steels and 12 chrome steel and nickel-based alloy. And the LSP system has been developed and applied to components of VWRs and the PWRs as a preventive maintenance against stress corrosion cracking since 1999. As I said, recently we couldn't do the LSP to Japanese nuclear power reactor. However, recently we applied it to the American nuclear power reactor, PWR, in Arkansas 1. Yeah. And so another application regarding to fatigue issue, LSP was applied to inside wall of the connecting pinholes for low pressure steam turbine blades to improve fatigue characteristics and reliability. I think by integrating high-res super laser B-Boy with a quarter-century experience of LSP in Japan, we can provide various real-world applications of LSP in the nuclear industry with high quality and throughput that could not be achieved with traditional lasers. Thank you very much for your kind attention. That's all my presentation.
Okay, thank you very much, Dr. Sanon. Thanks a lot also for keeping perfect timing. So I will check with our colleague if there are some questions. So it's really... So far, I don't see any for this presentation. So with that, I would like to thank you and to all three presenters of our first block. Thank you very much to you all, even though small technical problems, but we are happy that we can actually bring you all the information and interesting results of research from around the world. So thanks a lot to you all.
Thank you very much. Sorry, my trouble before starting the presentation. I will attend the next year. I will. Thank you.
So, thank you. So we finish our first session, and now we would like to continue with the next session. As first presenter will be Jan Prehradný, who will actually talk to you from our center. So I would like to welcome Jan. Hello, good morning, and yeah. If you can say, please, few words about yourself, we can put the presentation on screen.
Thank you. Hello, ladies and gentlemen. Let me introduce myself. My name is Jan Prehradný. I'm head of Nuclear Fuel Cycle Department here in Research Center Rzesz. And so, okay, thank you very much. I would like to introduce you some our research activities of our Nuclear Fuel Cycle Department. Our activities were supported by both of the projects SUSEN and R4S. Our activities are divided into 5 basic groups. The first is deep repository research activities. The second is spent fuel reprocessing, radioactive and hazardous waste treatment, threshold concentration analysis, and several accident studies. The first part focused on the deep repository research is our advanced corrosion research. We specialized on long-term ensuring of an anaerobic environment of corrosion experiments, evaluating of corrosion parameters, cultivation of aerobic and anaerobic organisms in bioreactor under specific conditions. For this purpose, we have 4 anaerobic glow boxes, which are able to reach very low oxygen concentration under 1 ppm. We are able to prepare samples in inert atmosphere and evaluate corrosion parameters using electrochemical methods and evaluate migration parameters in inert environment. Thanks to our infrastructure with a lot of microscopes, optical and electron microscope, we are able to very deeply evaluate the surface of our samples. On this picture, you can see this, the surface of the steel after experiments in anaerobic glow boxes. The second part of our research focused on the deep repository is our advanced material research. We are providing characterization of solids by gas sorption and mechanical test of geopolymers and cement materials. In our laboratory, we are able to analyze particle size, comprehensive fluxor and tensile strength test using a hydraulic press, measure specific surface porosity, pore width distribution and volume of the pore by gas sorption, and describe the geological core. Together with that, we prepare the samples for many of analyses like crushing, grinding, cutting, or other chemical modification. And we are able to evaluate materials degradation in various environments. Next activities are the development of special advanced inorganic materials like geopolymers and shielding materials for nuclear safety. Second part of our research program is a spent fuel reprocessing. We develop a method of fractional distillation of fluorides. In this method is a separation technology based on the direct fluorination of spent nuclear fuel with fluorine gas and the separation of volatile products from non-volatile products. This separation technology was developed and verified for our Japanese partners from Marubeni and Hitachi. Second part of activities in this laboratory is our corrosion and material test in fluoride meltings. We are providing stationary and dynamic corrosion tests in molten fluoride salts under various conditions with a focus on research of materials for reactor of fourth generation. For this purpose, we have built special boxes with inert atmosphere and special flyby loop, which is able to provide stationary and dynamic corrosion test in fluoride melts. These tests are providing the individual components for melt and fluoride salts, and we are developing and verifying methods for preparation of special fluorides and preparation of liquid fluoride for the irradiation experiment. Our loop and special boxes enable us to provide long-term and short-term corrosion tests in fluoride melts up to 1000 degrees C. Thanks modern diagnostic and analytical methods like SIMS, FIPSEM, EDS, VDS, and other optical microscopy, again, we are able to very deeply characterize the samples before and after experiment, so we obtain very interesting results from this research. Third part of our research is specialized on optimization of treatment and disposal of hazardous waste. We have very advanced research program to support the nuclear fuel cycle, including technologies for the treatment and disposal of hazardous waste. For this purpose, we have a system of two separate technological circuits, enabling optimization of liquid, solid, and semi-liquid waste processing with emphasis on thickening, crystallization, and final solidification in solid product. We have two experimental equipment. The first is experimental technological line, ETL, and the second is molten salt oxidation. In ETL, we have very interesting research of vacuum thickening of liquid waste. We are using evaporator, crystallizer, separation centrifuge, vacuum dryer, and we optimize the process with low temperature crystallization and optimization separation processes. In this experimental technological line, we develop matrices for solidification of hazardous and radioactive waste. The second equipment is molten salt oxidation line. This equipment enables to develop high temperature mineralization of solid organic waste and flameless combustion of organic liquid and semi-liquid waste. We research of the pyrolysis organic substances in salt melt. Both of these equipment enable to simulate presence of ionizing radiation source. There are pictures from experimental technological line after solidification process and molten salt on the end during the end of experiment from molten salt oxidation equipment. Regarding this area of our research, we have very interesting research of evaluation of the ion exchange masses and sorbents. We are using the most modern methods for testing ion exchange materials in order to determine the current ion exchange capacity or damage to sorption materials. We are determining total capacities and usable capacities of ion exchange masses. We are measuring penetration curves, ion-X bead integrity, and particle distribution of ion exchange and other sorption materials. We are measuring pressure loss of sorption materials in the whole system, and we are developing the field, the creation methodologies for the operation of ion exchange filters. Other area of our research is our laboratory of element and isotopic microanalysis. We are providing analytical support for research and services for the nuclear and non-nuclear industries, academia, and government agencies. We are developing microstructural analysis of chemical and isotopic composition of samples of various materials using advanced analytical methods. We are researching analysis of solid and liquid samples of various materials using radiometric methods, and we are developing the methodological procedures for the analysis of particles of nuclear materials to support nuclear safeguards and nuclear forensics analysis and other types of microscopic particles for environmental monitoring. More about this research will be presented in next presentation by my colleague. Last activity in our laboratories are specializing on high temperature melting of materials. We are using induction melting of metallic and non-metallic materials using technology enabling high purity of the final product. It means called crucible. We are researching the phase diagrams, measuring of liquidus and solidus temperature, and we are researching chemical physical properties of molten materials at high temperatures. In this laboratory, we are modeling several nuclear accidents and behavior on properties of corium, research of the behavior of corium during its discharge, and interaction between molten material and other foreign materials like structural material of the reactor, for example. These activities are developing with our colleagues from Japanese, and you will hear in our research from our colleagues from JEA from Japan. I thank you for your attention.
Thank you, Jan. Thanks a lot for this presentation summarizing what the whole doing our department related to fuel cycle. So thank you very much. So far, I don't see here any question. So if anybody from the audience has a question, please write them in the chat. Yeah, we can then continue with our presentations. And there's another colleague of mine, Jan Lorenčík, who is going to tell you more about the analysis of microscopic particles containing uranium and plutonium for the nuclear safeguards. Jan is also one of the experts from the same department, so you could hear already a few words what they are doing related to the research for the international agency. So, and today he will tell you more in details about his work.
Hello, everybody. Thank you, Jana, for a nice introduction. Before I start off my talk, I would like to mention my collaborators, Kristina Sielska, Klara Řezankova, and Ivan Elantiev, who made a substantial contribution to the work which I am going to present. Here's my presentation outline. I will start with the introduction to the environmental sampling for safeguards, and the main part of my talk will be about analytical procedures which we developed at my research group at CVR. What is environmental sampling for safeguards? It is a chain of steps towards verification of the adherence of member states to the Non-Proliferation Treaty. It is based on the assumption that every nuclear process, no matter how it is designed or how it is leak tight, emits small amount of material, mostly in the form of micrometer-sized particles, into the environment. It involves several steps: collection of samples of material in the environment of a known or suspected nuclear facility, and also sophisticated analytical techniques. And once those techniques produce results, the results need to be interpreted, and there are various evaluation tools for that. It is proven to be one of the most powerful tools for nuclear verification. The history of environmental sampling for safeguards dates back to the aftermath of the first Gulf War, when the inspectors of the IAEA came to the nuclear installations which were damaged by bombing, and they were on a mission to obtain proofs of nuclear weapon program of Iraq. They cannot use conventional methods of verification of Non-Proliferation Treaty, which is physical checking of evidence of nuclear material, because everything was destroyed. So they improvised and used cotton towels to swipe surfaces of the nuclear installations. And after analysis using sophisticated analytical techniques, they found entire spectrum of uranium enrichment, including the highly enriched weapon-grade uranium. Thus, the contaminated towels helped to reveal the Iraqi clandestine nuclear program. What is the current status of the environmental sampling? It is a routine method used by IAEA, and it is one of the most powerful verification tools. The environmental sampling procedures or methods could be divided in two classes of methods or analysis: bulk analysis and particle analysis. Bulk analysis analyzes the whole sample, the swipes, so swipe which you can see on the top right corner as a whole. So in this analysis, the swipe is dissolved, and all particles which are on the swipe are analyzed as a whole. In this way, an average information is obtained about the nuclear material. On the other hand, particle analysis is
once again, apology, and thanks for your patience. Thanks also for patience of our presenter.
I think we are back.
Please.
So I will summarize what I have presented in my first part of the talk, and that was that I made brief introduction into the environmental sampling for nuclear safeguards, which is today a very important and effective verification tool of the International Atomic Energy Agency. And I described briefly a history of environmental sampling and provided some information related to that. And now comes the main part of my talk, which is about the analytical methods which we have implemented or developed at our company with the help of projects and in collaboration with IEA and JAEA, as you can see on this slide. So the very first step, as I already mentioned in my previous slides, is the collection of samples. We have made an environmental sampling kit, which you can see in the left column, and the main part of it are cotton swipes or cotton fabric, 10 centimeters by 10 centimeters, which are used for swiping the surfaces, as you can see in the middle of the slide. And at the end, we have a swipe, and you can see darker parts on the swipe, which are dust particles. Once we have that swipe, it is placed in a Ziploc bag. It is very important is coding and recording the place and time of taking the swipe. Now we have developed two methods of particle extraction from the swipe. We can name them dry and wet methods. The first one is described here. We use a plastic head connected to the vacuum pump, which sucks the air from the surface of the swipe together with the particles. The particles are carried by the stream of air and are deposited onto the substrate, which is placed inside the plastic head. That plastic head is called vacuum impactor. In the rightmost image, you can see taking particle extraction, which is made inside disposable glove box. It is very important to prevent so-called cross-contamination of our samples. This means contamination from the extraction from the previous swipe. And the wet method is based on inserting particles into a solution of ethanol and collodion. The particles on the swipe, or the whole swipe, or part of the swipe, is inserted into ethanol, and we use ultrasonic cleaner to release particles into the solution. Then we add collodium. It is used to glue particles on the surface so they don't so that we don't lose them during manipulation with the substrate. And we pipette the solution of particles onto silicon substrate, as you can see in the image. Then after drying, we have particles glued on the substrate. Now comes the step of particle identification. So we have tens of thousands of particles on the surface, and only few of them are particles of interest, that is, particles containing uranium. In case of SIMS, we use imaging capabilities of that instrument, and we use automatic particle search program, which divides the surface of the substrate into 500 micron by 500 micron fields, which is the maximum size for rastering of the primary ion beam. And we obtain ion images, we used ion images of 235 uranium and 238 uranium. So we obtained two sets of images for every field on the sample. There could be hundreds of fields, or even more than 1,000, depending on the size of the field and on the size of the sample which we analyzed. So on the left image, you can see those dots represent a single field. So as you can see, we inspected a circular area in this particular case. And on the right-hand side, you can see images of a single 500 micron by 500 micron field. You can see there 4 or 5 particles of uranium. And on the right-hand side, that image is after image analysis processing, where particles are identified by colors. So the outcome of this part of the analytic procedure are positions of particles containing uranium. In addition to that, we obtain a rough estimate of enrichment for every particle, because we set up the instrument for both 235 and 238 uranium. And also from the scatter diagram, which you can see on the right-hand side of the slide, we could identify at least 2 populations of particles. One, a major population, has enrichment around 1.6%, and the second one around 2.6%. So we got very first information which allows us to make decision on what particle we take for accurate analysis. Then the second method which we use for particle identification is the fission tracks. Here I would like to briefly explain the principle of the method. Here the particles on a substrate are inserted into a neutron fields. Thermal neutrons are coming from all directions and induce fission of uranium-235 in particles where it is present. And fission fragments emitted from those particles leave damaged tracks inside material around them. And besides the particles on the substrate, we have attached a plastic detector. Concretely, it is a Lexan detector. And this detector is transparent. And we remove that detector after the irradiation. And in etching solution, we enlarge the channels, the damaged channels, damaged tracks inside. And those tracks are big enough to be observable by optical microscope or even by unaided eye. So once we have those tracks, we can determine the positions of the particles and continue to the next step, the analysis in the mass spectrometer. We have developed our own innovative procedure. It involves creating a so-called fission track assembly, which is a sandwich of silicon substrate particles and Lexan, held together by plastic brackets, which you can see on the right-hand side. This fission track assembly is inserted into irradiation capsule and exposed to neutrons in our LVR-15 nuclear reactor. The dose which we use is about 10 to 15 neutrons per square centimeter. Here is the outcome of this experimental exercise. On the left image, we can see the fission tracks on the Lexan detector, and on the right-hand side, you can see the details. The fission tracks look like stars with the center which reveals the position of the uranium particle. So the outcome of this screening procedure are the positions of particles containing uranium, and in some cases, we can estimate the enrichment. Here you can see the results of one of our studies where we had particles of equal size, but of different enrichment. From the left, that was natural uranium enriched particle, 1% enriched and 3% enriched. And you can see that the size, the number of fission tracks is different as expected, and under favorable circumstances, we can also get information of enrichment from the fission tracks. Once we have positions of particles, we insert the sample into a mass spectrometer. Usually, or typically, mass spectrometers have sophisticated sample stages with a navigation system. So once we have the coordinates of particles, the individual particles could be easily found inside the mass spectrometer and placed onto an optical axis and analyzed. The outcome of the individual particle analysis are tables of concentrations for minor isotopes, uranium-234 and 236, as well as for uranium-235. And from that information, technological history and the history of manipulation with the particle exposure in the nuclear reactor could be inferred. It is important that those measurements are very accurate and that the uncertainties are low, so that the evaluators could, so that it could be useful for the evaluators. So who are the users of our techniques? National authorities for inspection of nuclear material. Recently, we entered into an agreement with the State Office for Nuclear Safety of the Czech Republic to provide measurements of microparticles of nuclear material. It could be used by investigators of nuclear material incidents and by international authorities for inspection of nuclear materials like IAEA. To briefly summarize, we have developed at CDR in Řeš new analytical capability for microscopic particle analysis for nuclear safeguards. The analytical methods used at CDR for environmental sampling are SIMS and fission track analysis have been described in my talk. And last but not least, by performing the research in this area and developing those analytical procedures, we created a knowledge base which could be used for other than nuclear materials, for the analysis of other than nuclear material particles. Last but not least, our research and development was supported by projects SUSEN, R4S. Also, we used infrastructure CANAM, supported by, administered or under the Institute of Nuclear Physics of the Czech Academy of Sciences. And also, we appreciate collaboration and help from the Central Analytical Laboratories of Nuclear Research Institute, our mother company. By that, I would like to thank you for your attention.
Okay, and thank you very much. Thanks a lot for this presentation. Actually, it's astonishing work for all of us with international importance. So thank you very much for presenting it and explaining your results and your methods. I don't see any questions here, but definitely if there are some, we will send them. We will send them to Jan, and he will be ready to answer you. So one more time, thank you for the presentation. And the last of this block, of this part this morning, is a presentation of our honored guest, Ayako Sudo from Japan, from the Japanese Atomic Energy Agency. I would like to welcome Ayako. Hello. I see there is a representation, so okay. We have you there. Okay. We also can see you. So good morning, hello, and thank you very much for participating. Please, you can start with your presentation.
Thank you for invitation to the conference. I'm Ayako Sudo from JA class, and it's 6 p.m. now in Japan, so good evening, everyone. Today I will introduce R&D activities for damaged core status analysis in JA class and collaboration with CVR on debris solidification. These R&D activities is for contribution to Fukushima Daiichi nuclear power plant decommissioning. Okay, it's today's content. First, I will introduce what JA and CLADS. And next, I will introduce the collaboration test with CVR. Especially, I will introduce the experimental result in 2016 liquefaction solidification test on simulated molten column. And as a currently work, larger scale test for iron-rich condition will be introduced also. And last is the conclusion and the future perspective. Okay. I am belonging to Collaborative Laboratories for Advanced Decommissioning, CLADS, in Japan Atomic Energy Agency, JEA. The CLADS is R&D base for domestically and internationally gathering knowledge for Fukushima Daiichi nuclear power plant 1F decommissioning. In 2015, JE established the CLADS, and currently Fukushima Environment Safety Center and CLADS are merged. And currently CLADS consists of 8 divisions, and I'm belonging to this core status evaluation division. The main task of CLADS is R&D activities related to decommissioning 1F based on the mid and long-term roadmap towards the decommissioning of 1F. Okay, next I will introduce our division, Core Status Evaluation Division. Core Status Evaluation Division consists of 4 groups: fuel degradation behavior analysis group, simulation test technology development group, corrosion analysis group, and radionuclides behavior analysis group. And each group conducts R&D activities from various viewpoints for decommissioning of 1F. I am belonging to simulation test technology development group, and the main task of our group is simulation test technology development of simulating 1F condition and fuel degradation modeling simulating 1F condition. And in this group, I am responsible for debris solidification analysis. And in this work, I collaborate with CVR to perform the solidification test using CVR facilities. This collaborative research is successfully carried out and great experimental results comes out. So I would like to introduce our collaborative test. I'm sorry. To understand the redistribution behavior of major components in the molten column simulated one condition, liquefaction solidification test of simulated column have been collaboratively planned and carried out with several experts. And this table is the test condition and the time schedule history of our collaborative test. Our collaborative test was started in 2015, and in 2015, Cometa facility in Shibuya was used. And since 2016, ISN facility has been used. Today, I would like to introduce the experimental result of J5 in 2016 using ISN facility. And as a current work, J12 in 2019 will be introduced also. Okay, next is motivation of our work. The molten column in the bottom of the RPV at 1F might solidify with a slow cooling rate. Generally, a segregation of components and phases is likely to occur during slow solidification. This is the same image of the grain growth of specific oxide phase under slow solidification. This heating test was performed in laboratory scale, and under such slow solidification, such grain growth of specific oxide phase or segregation of components is likely to occur. So for criticality assessment of one field debris, knowing the segregation of neutron absorber materials such as gadolinium and iron is particularly important. Gadolinium is important because gadolinium doped fuel is used in one reactor as a neutron absorber material. So gadolinium plays an important role for critical assessment of field debris. And iron is also important because a large amount of iron is contained in one field debris. So iron is also important for critical assessment. So in this collaborative test, liquefaction solidification test of simulated molten column in a laboratory scale has been performed. Such 1 kilogram large tests can be performed by using several facilities. So the important parameter in this test is as following 2 points: influence of cooling rate to the chemical characteristics of field debris and segregation tendency of iron and gadolinium in field debris. Okay, next is the test facility. The test was performed using ISN facility at REGE CVR, and it is designed for melting and solidification in an induction furnace with a cold crucible. And using this system, simulated column materials with mass of 1 or 2 kg can be heated at up to 3,000 degrees C. Mr. Dr. Zhang introduced this system in this section, and if you would like to more information about this system, please ask Zhang or Shibuya expert Benz or Marek Igor. This large-scale heating system is so useful to simulate the solidification of one condition. And additionally, in this particular collaboration test, the moving unit was attached to the facility for the gradual solidification of simulated column. Using this moving unit, the melt in sample stage moves below the heating unit slowly and solidify gradually from below. It means this unit was useful in understanding of progress of the solidification of the melt and the forming of the solidification structure. It means it's useful to understand where is the final solidification of melt or where is the later solidification, area solidification of a melt. And in 2016, I visited CVR, and the test was performed with discussion with CVR experts. He's Dr. Pozniak, Professor Pozniak. And the next is the test condition. This is the composition of starting mixtures of heating test, J5 heating test. As the starting materials, rhenium oxide, zirconium oxide, gadolinium oxide, FeO, and simulated FP was prepared in powder form, and the total mass of powder was approximately 900 grams. And this is the temperature history of melt surface during heating test, and the experiments are conducted in an air atmosphere. And the melt surface temperature was in the range of approximately 2,300 degrees C. And after stabilization of the melt temperature, the sample stage was moved below, and cooling and slow directional solidification was performed by moving it. The sample stage was moved below, and melt was solidified from below slowly. Next is the result. This is the cross-sectional view of the ingot, solidified ingot after split. And this cross-sectional view shows two zones, zone 1 and zone 2. The bottom region, zone 1, seems layered stripe structure, such stripe structure, and the zone 2 has no layered structure, and it has several shrinkage cavities and upper crust. This is a semi-image of this J51 region, and it shows zirconium, rhenium, iron, gadolinium oxide polycrystalline structure, and the composition was similar to the starting composition of J5. Next is a discussion about the solidification progress of the melt. During the initial downward deplacement, the melt may have solidified from bottom to middle, and the layered structure zone 1 was formed. After that, the surface of the melt solidified and the upper crust was formed. Then the remaining melt was solidified toward to the inner region, forming shrinkage cavities, and zone 2 was formed. It means the final solidification region was estimated to be near the center of zone 2, about 2.5 centimeters from bottom of the ingot, near here. Okay, next is a discussion about the segregation tendency of iron and gadolinium. To see the segregation tendency, the several pieces are cut from the central axis, cut from bottom to top, and the concentration of iron and gadolinium was compared from bottom to top. This is dependence of iron and gadolinium concentration on sample heights. This 0 point is the bottom of the ingot, and this 3.2 centimeter is the height, top of the ingot. The iron concentration shows its maximum value at 2.7 centimeter, and it is near the final solidification region of the melt. On the other hand, the gadolinium concentration shows its maximum value at 0.5 centimeter, and this is near the area solidification region, bottom of the ingot. So experimental result indicates iron concentrates to final solidification region, and the gadolinium concentrates to area solidification region. This segregation tendency of iron and gadolinium is so useful information for criticality assessment of one-field debris. Next is a discussion about the segregation tendency of iron using phase diagrams. This is a phase diagram of UO2 FEO system, and it is a phase diagram at high temperature. When liquid is solidified as temperature falling, the solute elements is distributed to solid and liquid. And when the liquid is distributed to solid and liquid, the concentration of FeO of solid is CS, lower FeO content, and the concentration of FeO of liquid is CL, higher FeO content. And the microsegregation of Fe to liquid is occurred. And during solidification, this microsegregation is repeated. And finally, the macro segregation of iron to residual melt inner region is occurred. This is the Zeta FeO system phase diagram, and the tendency of segregation of iron is similar to U2 FeO system. This estimation using phase diagram is well accordance to experimental result. Okay, next is I will introduce current works solidification test on simulated molten column with iron-rich compositions. To observe the microscopic segregation and Fe behavior in life condition, a larger scale test with a mass of 2 kg with iron-rich composition is subject in 2019 and this year. Heating test and preliminary analysis was performed in 2019. This is a view of the ingot, solidified ingot after split and semi-image. The complex phase separation is occurred with iron rich composition, but the segregation tendency of iron is well accordance to previous works. Currently, additional analysis will be performed in this year. Okay, this is conclusion of this presentation. The solidification test collaboratively planned and carried out with several experts. The segregation behavior of iron and gadolinium during the solidification was investigated. The concentration of Fe increased in the final solidification region. On the other hand, the concentration of gadolinium increased in the earlier solidification region. Gadolinium segregation could significantly affect the criticality of fuel debris. Our result could propose that gadolinium concentration in center region of debris needs to be carefully investigated. And as a current work, a larger scale test with iron-rich composition was performed. Detailed data of iron segregation is expected, and now semi-electrical analysis is ongoing. Okay, last is a perspective. Currently, CVR and JA are continuing discussion of the future plan. Now we are considering solidification and segregation from solid liquid mixture, interaction between molten fuel and structural materials, and segregation of components of column containing concrete. And this plan is simulating F unit 1, 2, 3, respectively. So thank you very much today, and I would like to thank for Dr. Pozniak, Benz, Marek from CVR for their scientific and warm supports. Thank you for your attention today.
Okay, thank you very much for your presentation. It was very clear and very interesting results of the work, which are also in collaboration with our institute, practical work on maybe not so easy topic as a Fukushima Daiichi accident and follow-up. So, but anyway, it's very useful work, and we are definitely happy that we can collaborate all together and we can support your research. So in this moment, I don't see any question on the panel. So we can just give a few seconds because there is some delay. So and then yeah, we will finish this this part of our conference. I would like to thank you and all the presenters one more time. Thank you for your time. Good evening in Japan. So and I hope to see you soon when it's possible in our institute. And meet again in person. So so far no questions. So thanks a lot. If anyone from presenting people would like to say something, go ahead. But yeah, okay.
Okay.
Okay. No, I don't see any raised hands. Okay. So. Thank you very much. Now on our program is the coffee break. So yeah, grab your own coffee and we will see you, or we will hear, you will see us in 11:50 when another part of our conference will start. So thank you for your presentations to our people who are presenting, and thanks for audience for listening us. So, and we are back in 11:50.